Today we are going to talk about rational functions. By the end of this video, you should be able to find equations of all asymptotes and state the intercepts, domain, range, and end behavior. First, we're going to review some things from Algebra 2. A rational function is a function of the form f of x equals p of x over q of x, where q of x does not equal 0. So basically it's a fraction. Our parent graph is f of x equals 1 over x. Rational functions have asymptotes, which are lines that the graph approaches. Generally, the graph does not cross an asymptote, but it is possible to. So, if you think back to Algebra 2, you have a vertical asymptote where the denominator equals 0. So if we plug 0 in for x, we end up dividing by 0 for this function, which cannot happen. So we have a vertical asymptote at x equals 0. This also means that we are not allowed to plug in 0 when we start talking about our domain. So our domain is going to be x such that x does not equal 0. Every other number is fine. We just can't plug in 0. Rational functions also generally have a horizontal asymptote. We'll look at those rules in a minute. For this function, the horizontal asymptote is y equals 0. And for this function, our range will be y such that y does not equal 0. Now, if you make a t-chart and find a whole bunch of points that'll be on this function, you'll get points like 1/2, 2, 1, 1, 2, 1/2, which will give you this half of the function. And if you plug in some negative numbers like -1/2, you'll get -2. -1, you'll get -1. And if you plug in -2, you get -1/2. And that'll give you this other branch of the function. As you can see here, we do not have an x-intercept or a y-intercept. One hint that would have told us that is that our vertical and horizontal asymptotes are on the x and y axis. So we have no x-intercept for this function and no y-intercept. In Algebra 2, you also talked about end behavior, where you look and see what happens at the ends of the functions. For most rational functions, we can write this as one statement as x approaches positive or negative infinity. F of x approaches. So if you look at the right end and the left end, both ends of the graph approach the horizontal asymptote, which is 0. If by chance the ends are going in different directions, you will have to split up the end behavior into two statements. As x approaches positive infinity, what happens? And as x approaches negative infinity, what happens? A new thing we're going to talk about is asymptotic or middle behavior. What is happening around the vertical asymptote? The way we write this is as x approaches the vertical asymptote, which is 0, then we need to talk about on the right side, which is the positive side, and the left side, which is the negative side. So, as we get closer to 0 from the right, so I'm going to start on the right and get close to 0, our graph is going up. It is approaching positive infinity. If I start on the left and get closer to 0, the graph is going down, so it is approaching negative infinity. So that's how you write the asymptotic or middle behavior. Now, let's take a look at the official rules for asymptotes. Vertical asymptotes occur at x values that make the denominator 0. So to find these, you want to make the denominator equal to 0 and solve for x. Your vertical asymptotes are equations of vertical lines, so they will be x equals a number. Horizontal asymptotes are the tricky ones. You have several different rules. It depends on the degree of the numerator and denominator. Remember that the degree is the highest exponent. So, if the numerator degree is less than the denominator degree, then your horizontal asymptote will be y equals 0. If the degrees are equal, you need to divide the leading coefficients. And you'll have y equals a number. If the numerator degree is greater than the denominator degree, you do not have a horizontal asymptote, but you might have a slant asymptote. Depending on which class you were in last year, slant asymptotes might be a new concept. A slant asymptote occurs when the numerator degree is exactly 1 more than the denominator's degree. And you have to find your slant asymptote by doing long division. So let's take a look at a few examples. First, we have a of x equals 2x plus 1 over x plus 1. To find our vertical asymptote, we need to set the denominator equal to 0. So if we have x plus 1 equals 0, and we solve it, we get x equals negative 1. So that is our vertical asymptote. For the horizontal asymptote, we need to look at the degrees. Since both the numerator and denominator are linear functions, they both have a degree of 1. So they are the same, so we need to divide the leading coefficients. The leading coefficients are 2 and 1. So our horizontal asymptote is y equals 2 divided by 1, or 2. For our x-intercept, we want to set the numerator equal to 0 and solve. So if you have 2x plus 1 equals 0, you solve that, you get x equals negative 1/2. So that is our x coordinate. So negative 1/2, 0, is our x-intercept. For the y-intercept, we want to plug in 0 for x. And then just simplify, which gives us 1. So 0, 1 is our y-intercept. Okay. So from here, you need to sketch your graph. The x and y-intercept tell us where this branch of the function is, but we don't have any points in the top left-hand corner. So if you need some more points, you can go to your calculator. Just go to y equals, type in your function, and then you want to go to the table, which is second graph. You want to look for integer points. So negative 2, 3 would be a good point to use. And we can just sketch our curve through that point. Now we need to look at the domain and range and end behavior. Our domain is going to be everything except the vertical asymptote, so x, such that x does not equal -1. Our range is going to be everything except the horizontal asymptote, so y such that y does not equal 2. If we look at our end behavior, both the left and right end are approaching the horizontal asymptote, so we can write as x approaches positive and negative infinity, a of x approaches the horizontal asymptote, which is 2. If we want to write our asymptotic behavior, as x approaches the vertical asymptote, which is -1, from the right, and as x approaches -1 from the left. If we start on the right and get close to the asymptote, we are going down, so we're approaching -infinity. And if we start on the left and approach the vertical asymptote, we are going toward positive infinity. Next we have b of x equals 4 over x squared plus 1. When we try to find our vertical asymptote, we need to set the denominator equal to 0. So if we have x squared plus 1 equals 0, and you try to solve that, you get x squared equals -1, so x is the square root of -1, which is I, which we don't have a vertical asymptote. For the horizontal asymptote, we need to look at the degrees. The degree of the numerator is 0 because there are no x's. The degree of the denominator is 2. So our horizontal asymptote is going to be y equals 0. For our x-intercept, we set the numerator equal to 0 and solve. We just get 4 equals 0, which is not true. So there is no x-intercept. For the y-intercept, we plug in 0 for x, so we get 0, 4 as our y-intercept. If you need to write that out to figure out the y-intercept, that's fine. Now we need to sketch in our function. We don't have a whole lot of information here, so let's go to the calculator. So we see that it looks a little bit like a hill. The high point is at the y-intercept, and then it gets closer to the asymptote on both sides. So if we sketch this in, it will look something like this. So our domain, since we had no vertical asymptote, our domain is going to be all real numbers. We need to look carefully before we find the range. The lowest that our graph goes is it gets very close to the horizontal asymptote of 0. The highest that the graph goes is 4. So I'm going to write my range in interval notation for this problem just because it's a little bit easier. If you want to write it in set notation, go right ahead. Then our end behavior. As x approaches positive and negative infinity, b of x approaches the horizontal asymptote on both ends, which is 0. Now for our last graph, we have c of x equals 2 over x minus 1 squared. Our vertical asymptote is where the denominator equals 0, which is x equals 1. For the horizontal asymptote, we look at the degrees. The degree of the numerator is lower than the degree of the denominator, so our horizontal asymptote is y equals 0. For our x-intercept, we would set the numerator equal to 0, which gives us 2 equals 0, so there is no x-intercept. For the y-intercept, we plug in 0 for x, so we get 0, 2. I'm going to go to the calculator to get an idea of what our graph looks like. Okay, and then I'm going to sketch that in. So we just sketch in our curve here. Then we need to find the domain, which is going to be everything except the vertical asymptote. So x such that x does not equal 1. The range here, again, we need to be careful. The lowest that the graph goes is it's getting really close to the horizontal asymptote of 0. And then as you get close to that asymptote, both branches of the function are going up to infinity. So our range is going to be 0 to infinity. Our end behavior, as x approaches positive and negative infinity, c of x approaches the horizontal asymptote, which is 0. And if we want to take a look at the asymptotic behavior, as x approaches the vertical asymptote, which is 1, from the right, and as x approaches the vertical asymptote from the left, from the right, the function is going up toward positive infinity, and from the left, the function is also going up toward positive infinity. So there's our asymptotic behavior. The last thing I want to look at today is slant asymptotes. So if you look at the degree of the numerator and denominator, the degree of the numerator is 2, the degree of the denominator is 1, which means we will have a slant asymptote. So all we are going to do here is find the equation for our slant asymptote. We are not going to graph this. We'll worry about that in the next video. To find the slant asymptote, you need to do long division. So I'm going to start by writing this out like a division problem that you would have done in 4th grade. When we do long division with polynomials, we only want to look at the first term. And we want to ask ourselves, what is 5x squared divided by x? Well, that's just 5x. Then we're going to follow the steps for long division that you learned in elementary school. We are going to take 5x, multiply it by x plus 1. We need to make sure we distribute. Then we need to subtract this from 5x squared minus 3x plus 2. So I'm going to change the sign of these and add them together. We get negative 8x plus 2. Again, I'm only going to look at the first term, and I want to know what is negative 8x divided by x? It's just negative 8. Then, negative 8 times x plus 1. I need to subtract, so I'm going to change the signs and add. So if I was just dividing these polynomials, 10 is my remainder. So if I'm just dividing, the answer would be 5x minus 8 plus 10 over x plus 1. For the slant asymptote, we only care about this part of our answer. We do not care about the remainder. So our slant asymptote is just y equals 5x minus 8. Let's look at one last example. Here we have 3x to the fourth minus x squared over x cubed minus x squared plus 1. So our degree for the numerator is 4, the degree for the denominator is 3, so we have a slant asymptote. So let's go ahead and do our division just like the last problem. Now, there's one thing in here that's going to be a little bit problematic. We are missing some terms. So I'm going to go ahead and add in 0x cubed, 0x, and 0, just so we don't lose track of those places. Now, we're going to look at the first terms. What is 3x to the fourth divided by x cubed? That's just 3x. Now I'm going to multiply 3x to x cubed minus x squared plus 1 and make sure I distribute. Since I need to subtract, I'm going to change the sign of each of these and add. Again, I only want to look at the first term. So what is 3x cubed divided by x cubed? That's just 3. Now, I could stop here because I have a linear equation right here. I have 3x plus 3. But just so we don't get into any bad habits and you don't make a silly mistake that you could have caught, I'm going to do a tiny bit more work. I'm going to go ahead and distribute the 3 over here. Change the signs and subtract. Now, because the degrees of these 3 terms are less than the degree of this part right here, we know that we are done. So that's a good way for you to double check your work so you don't make a silly mistake. So our slant asymptote is just 3x plus 3.